where the bottom is, 0, is where we're going to have a vertical. The thing that we don't know yet, and the hardest thing in this whole thing, is how do we figure out horizontal asymptotes? So you're going to have to wait. I'm going to have to slowly get into this. All right? So here are the steps. You ready for steps? I'm going to write them down, and you're not going to know what the hell I'm talking about for most of these. And then as we work through an example, you'll see it hopefully start to come to light. All right? All right, first step, right? How to sketch rational functions. Remember what I just said. For now, just copy this down. As we work through examples, you'll see it hopefully come to light. First step, we're going to find the x-intercepts of the rational function. That's the first step. Now, how do we do that? What we do is we take the numerator and set it equal to 0. All right? We just figure out where the numerator is 0. Wherever the numerator is 0 is where we're going to have x-intercepts. All right? Now, when you do this, just remember these are points on the x-axis, right? That's what an x-intercept is. It's points on the x-axis. After you've done that, we go to step 2. Step 2 is we're going to find the VAs, vertical asymptotes. I'm not going to write that. I hate writing that over and over. So I'm just going to put VA for vertical asymptotes, all right? So we're going to find the vertical asymptotes. How do we do that? Well, all we have to do is take the denominator, set it equal to 0, and solve. That's actually not that bad now that you see the steps, right? Just set the top to 0, boom, solve. Set the bottom to 0, boom, solve. And you've got almost half of this thing done. All right, the third step is to find, I need to tell you what these are. Forgot. What are these? Well, these aren't points on the graph, right? What are these? These are vertical barriers, right? Well, let's say vertical dotted barriers, because when we draw them, they're going to be dotted lines. Dotted barriers. Right? That's what they are. They're vertical dotted barriers. And what does my function do as it gets closer to this barrier? It either dives down or it takes off up, okay? So I'm going to put here, these are vertical dotted barriers that force the graph up or down. Vertical dotted barriers that when I get close to them, my function goes up or down. Can't cross the vertical barrier, cannot cross it. Okay? You cannot draw a function that goes through the vertical barrier. It's going to have to either go up or down. All right, next step. Find the horizontal asymptotes. All right. And this is the one I told you is the part that sucks. All right. To find the horizontal asymptotes, the thing that makes it so crappy is that there are 3 different scenarios that could happen. There are 3 cases. Oh, well, you know what I should do before I do that? Let me tell you what we're going to do. So to find the vertical asymptotes, what you do is you compare the degree of the numerator to the degree of the denominator. Remember, I said that a rational function, right? I told you already that a rational function is just a polynomial divided by a polynomial, right? That's what I said. And so if you look at the numerator by itself, that should have a degree, right? A highest power of x. And then that should have a highest power of x. What we're going to do is we're going to compare those powers. We have the power of the top and the power of the bottom. We're going to look at those two numbers and we're going to compare them. And when you compare two numbers, there's only three things that could happen. Either the numerator is smaller than this, the numerator is bigger than this, or they're the same numbers. That's the only things that can happen. So once you do that, you have three cases. The first case, case 1, is that the numerator degree is smaller than denominator. The second case is that the numerator's degree is bigger than the denominators. And the third case is that they're equal. I'm going to give you 3 examples today. Each example I give you is going to be an example of one of these. So what I'd like for you to do is, for now, we're going to leave this kind of like unknown. What do we do in these cases? But the first example is going to be this one I'm going to do. So I'm going to tell you right now what happens if you have case 1. In this case, y equals 0 is your horizontal asymptote. Again, if this doesn't make sense, don't worry. We're going to do an example, all right? Just write that down, and then when we do my second example today, I'll do this case, and I'll tell you what happens then. And then I'll give you the third case, and I'll give you an example and tell you what happens then. Fourth step, 7 steps to go. You ready? I'm kidding. There's only a few more. Fourth step, plot all the information. Plot or sketch all information thus far. So we're going to do a graph, and on that graph we're going to draw our x-intercepts. We're going to draw our vertical asymptotes. We're going to draw our horizontal, whatever's happening here, we're going to draw it. We're going to put it all onto a piece of paper. And once we've done that plotting, the next step is test points. Test points. And I'm going to leave this as an open question right now. I'm not going to tell you what this means yet. But we're going to do this, and then our final step is going to be to sketch it. So leave this as open, all right? Test points, what the hell is he talking about? I will show you. There it is. Those are the 6 steps to graph a rational function. Find the x-intercepts, find the vertical asymptote, find the horizontal asymptote, put all the information down, do some test points, draw your final picture, you're done. All right? Is it making you sick? Yeah, I feel it too, yeah. All right, let's do a problem. All right, first example, f of x equals, we're not going to do the one we started class with. I'm going to do something else. I'll make it similar though. How about this? No, let's not. X plus 1 on top. Let's do x squared plus, you know what, make it x plus 2, sorry, on top. X squared plus 4x on the bottom. I would like to know what that graph looks like, okay? I'd like to know what the sketch of that looks like. Step 1, find the x-intercepts. So what am I going to do to find the x-intercepts? Set what to 0? The numerator, which is x plus 2. Set it equal to 0. That's a linear equation. Everyone here should have no problem solving that, right? Set that equal 0, move the 2 to the other side, subtract 2 on both sides, you get -2. What is that going to be on my graph? When I draw that, what is that? What is it? What is it? X-intercept. So it's just a point, right? Like a dot on the x-axis. Got it? Okay. Now, second step. I want the vertical asymptotes. How do we do that? Set the bottom, right, to 0. Set the bottom to 0, the denominator. X squared plus 4x equal to 0. All right, how are you going to solve that? What's that? Factor, right? Factor. Okay, so how can you factor this? What's our first step for factoring anything? GCF, right? Pull out GCF. So what can come out of both of those? X. You're left with x plus 4. And now you set each of those equal to 0. So you get two solutions here. Right? There's two answers. 0 and -4. What are these on my picture, on my graph? You all right with that? Yeah? What are these on my graph? Are these x-intercepts? No, these are my vertical barriers. And that means I have two of them. I have two vertical barriers. Okay? Third step. Horizontal asymptotes, right? Horizontal asymptote. To find that, what do? Compare the degree of the numerator to the denominator. What is the degree of the numerator? 1. The degree of the numerator is 1. You'll see that in red? What is the degree of the denominator? 2, right? It's the highest power of x that we see. All right, which one's bigger? Which one's bigger than the other one? Denominator's bigger than numerator. Or you could say numerator is smaller than denominator. Isn't that case 1? Okay, so this is case 1. This is case 1. Because the numerator's degree is smaller than the denominator's degree, because the numerator's degree is a 1, and the denominator's degree is a 2, right? So what happens in this case according to what I told you? What's going to be our horizontal asymptote? Y equals 0. So y equals 0 is our horizontal asymptote. Now, y equals 0, you have to know what the hell y equals 0 means. Y is the y coordinate, right? Y is the y coordinate. So we're saying our y coordinate is 0, which is really the x-axis, right? If this is our graph, y equals 0 is right there. This is saying that we have this dotted line at the edges of our graph at y equals 0. So I'm going to put here, remember these are dotted edges only. You'll see as I draw it what I mean by that. All right, we got 3 steps down. Fourth step. What's my fourth step? Plot all the information, right? Put everything down. So here comes my picture. Give myself plenty of room here. The graph of the function I'm about to draw, I'm going to graph in black. All right? Whatever's in black is the actual function. I have an x-intercept at -2. So I'm going to go to -2 and put a dot. Okay. That takes care of the first piece of information, right? Now, I have vertical asymptote. I have 2 of them, one at 0 and one at -4. These are vertical barriers, right? So I better not put them in black. They're not part of my graph. They're to help me graph. So at -4, I'm going to place a vertical dotted line like this. And then also at 0, right? And it's going to suck to have to draw a dotted line on top of a solid line. So what I'm going to do is this instead. Over here, I'll put dotted up here like this. But I'm also going to do like little dashes, little angle dashes so you can see it. You'll see we have 2 vertical asymptotes? No? One at 0, one at -4. Okay. Third thing, horizontal asymptote. Got this? Y equals 0, which is the x-axis. Very important. The dotted line I'm going to draw is only at the edges. Only at the edges. So I'm going to draw dotted out here and dotted out here. Okay, do you remember when we were doing polynomials, I had that table and it told you like left and right hand behavior, what goes up, what goes down? Yes? But that only told us about what's happening at the edges. this dotted line right here is only telling us what's happening out at the edges. This is the thing where our graph goes down towards it, like this. And over here, it's going to go in like this. It tells us nothing about what happens in here. So do not draw a dotted line all the way across. It'll confuse you, trust me. Just draw it at the edge. Yes, just for the horizontals. The verticals are true barriers. These are true walls. We can never punch through them, all right? As you draw from left to right, you can't go through them. These, I like to treat these, I call them magnets. You know, a magnet like attracts, it can repel too, but you know, most time you think a magnet pulls something towards it. This is like a magnetic line that pulls our graph towards it. All right, that's the general like structure of the graph. And notice we only know of one point on this graph, right? That's the only point we know for sure lives on this graph. We don't know anything else about this graph. So now we go to step 5, which is what? Test points, right? And I told you I didn't tell you what that step was. So step 5, test points. So the idea here is this. I know a lot about the graph, but there's a lot I don't know. So what I'm going to do is I'm going to pick some points to help me graph the rest of it. And the points I pick are kind of up to me, but kind of not up to me. They have to be helpful. Like the points have to actually give me some information. So think about this. To the left of this vertical, I don't know anything, do I, about my graph? So wouldn't it be useful if I pick some sample point over here, maybe like that's -4, maybe I pick -5, and I plug that into the function, then I would know if I have a point above or below, wouldn't I? You'll see that? So why don't we use test point, let's use -5 as one of our test points. That should give us some information about over here. And then here, look, between this vertical and this x-intercept, I don't know if my graph is above or below. So why don't I pick a test point right here? What's a good one right there? That point right there, right? -3? That should give me some information about what's happening between these two. What do you think my next test point is going to be? -1. Notice I'm putting little X's here. I'm not putting dots. I'm putting X's here and circling the test point so that you don't accidentally think it's an x-intercept. These are just references, right? So -1, I'm going to test that point. I'm going to plug that into the function. It's going to give me a dot above or below. Do I need any more? What do you think? Maybe one more on this side, right? Over here on this side, because I don't know what in the heck's happening over here. So I'll pick anything I want. Any number you want over here. What do you want? Anything. What, 3? I heard 3. 3. Someone said 2. 2 would work as well. So I have, how many test points do I have? I have 4 test points. See that? I have 4 test points. Okay. How many test points will you have, right? It's going to depend on the problem. We have 4 right now, right? How many x-intercepts do we have here? 1. How many verticals do we have? 2. That's 1 and then 2, that's 3, right? We have 4 test points. You will always have one more test point than the total number of x-intercepts and verticals together. All right, you will always have one more test point than the number of verticals and x-intercepts together. I'll write that down in a minute. All right, what do we do with these test points? Plug them into the original function. Yeah, this is going to suck. I'm going to have to take -5 and plug it in right here, right? Plug it into this. Get my calculator out. -5 plus 2 over -5 squared plus 4 times -5. And look, I admit, you're going to get an answer, okay? You're going to get an answer. But really, all I care about is whether or not this point is above or below the x-axis. That's really all I care about. Is the point up here or is it down here? That's all that matters to me, because that'll give me the general shape of the graph. So I know here I get let me see, I get a negative 3 on top. On the bottom, I think it's 25, and then these multiply is minus 20. So you get negative 3 over 5. You get negative 3/5, which is negative 0.6. Did anyone get that on their calculator? Negative 0.6, right? Y'all buy it? Okay. I got to do this 3 more times, right? Kind of a pain, but that's what you got to do, okay? Now, there's a small shortcut. You don't have to take the shortcut. If you're happy right now, you can just start plugging these numbers in, okay? F of negative 3, plug it in, you get negative 3 plus 2 over negative 3 squared plus 4 times negative 3. You can figure out what that is, right? If you want a small shortcut, here's what you can do. Go back to the original function and rewrite it, but factor the denominator. Remember how we factored it earlier? Remember how we did that? We took out an x. I'd like for you to think about what this would be. This right here. I'd like us to do this problem again, but I'd like for us to do this instead. Watch, this is really cool. Not cool, it's just fast, all right? All right, so imagine if I plug negative 5 in, negative 5 plus 2, is that a positive or negative number? Negative 5 plus 2. Negative. So the numerator is negative, right? Okay, now, negative 5 goes here, right? So that's a negative number. Times, now what's negative 5 plus 4? Negative, right? So that's a negative number. So you have a negative divided by a negative times a negative. What are 2 negatives multiplied? Positive. So this is a negative over a positive. What's a negative over a positive? Negative. So what that tells me is that, I mean, here you know exactly what the number is, right? Negative 3/5. Here, I know it's a negative number. They both basically tell me the same thing. At this point, I have a point down here, right? At negative 5, I have a point below the x-axis. I find this faster than doing all this. Try it for this one. Let's see if this one works any faster. What would happen if I plug negative 3 into the top? Negative. On the bottom, negative 3. Here, negative 3 plus 4. Positive, right? Do y'all see that the bottom is negative and the top is negative? Negative divided by negative is positive. So without me actually even needing my calculator, I can tell you that that's a positive number. Okay, so you do the rest, right? I need to erase it because I need to come to this graph. All right, I'm going to put all this together. You ready? At negative 5, I got a negative number as an answer, right? So I'm going to come down a little bit anywhere I want. I'm just going to draw a dot. I'm drawing it in black because it's part of my graph. At negative 3, we got a positive number, right? So I'm just going to go up and put a point up here somewhere. And then at negative 1, I didn't show it. Okay, I didn't show it. But if you plug in negative 1, you're going to get a negative number. So it's going to be down here somewhere. And then at 3, if you plug 3 in, I'm not showing it, you would get a positive number, which means it would be up here. We're almost there. All right? I claim that at this point you should be able to graph it. You have everything you need. All right? You ready for me to do it? Let's start at the point right here, furthest point to the left. That point I know lives on my graph, yes? If I ask you to draw it out to the left, what are you going to do? Are you just going to start wiggling around here? What are you going to do? What does this tell you you have to do? What is this? Wasn't that like I told you that was like a magnet, right? Pulls your graph towards it. Our graph gets closer and closer without touching it. So I go towards the horizontal asymptote. Now, at that same point, we drew it out this way, right? It had to go up towards that. Turn around and now try and draw it that way, and what happens? Start drawing, and what? You got a barrier, right? And that barrier is going to force you either up or down, right? So is it up or is it down? Down. Why down? Why can't it be up? Is it a flip of a coin? Is it just you guess, you get to pick? Why can it not be up? Why can this not turn up and go like that? Why? Yes, if I draw this up, right? Imagine I did that. What if I did this like this? You just crossed the x-axis, didn't you? And this is the only place you're allowed to even touch the x-axis, right? That's the only place. So you've created an x-intercept that doesn't exist, which means you can't go up. And if you can't go up, then that means you have to go down. And so as I draw this, I'm just going to draw to the right and bring it down. Do you understand what I'm doing here? I'm just thinking through each point, what has to happen. Now, I actually do have to pick up my pencil, okay, and go to the next point, which is this one, and I even play the same game. As I go this way, what has to happen? Well, barrier, right? So either up or down. So can you go down? No, see, you're going to hit the x-axis again. You can't do that, which means you have to go up, right? So from this point, it's going to have to go up like this. And then I got to get from this point to the right, but I got to get to this, right? So I'm back in kindergarten here for just a few seconds. I've got to connect that to that to that, right? So I'm just going to connect. And then I have to continue drawing to the right, and then I have this barrier again, which is going to force me down because I can't turn back up because I can't have an x-intercept here. So all of that together makes me draw this. Are y'all processing all of that? Pick up your pencil. Last point. To the left, what happens? It's got to go up, right? Can't come back down. Can it do this? Could it do this? Why can't it do that? Why couldn't it turn away like that? Like, no, I don't want it. I'm going to go the other way. Yeah, very good. Then it would fail the vertical line test and it wouldn't be a function anymore. You have to remember that at the end of your picture, it has to pass the vertical line test. So it can't do that, right? It's got to keep going to the left, but it hits the barrier. It's like, shit, and it has to take off, right? And then what about to the right? That pulls it towards it, right? So it's got to get pulled down towards that. And there you go. That is the graph of that rational function. Y'all look depressed. It's depressing.
A way to know how many of those, like, you'll,
How many whats?
like the, you know,
How many? Well, here's what I can tell you. Because we had two verticals, I'm going to have like 3 sections, right? I'm going to have a section over here, section in the middle, section over here. If I had one vertical, I'd have like 2 sections. If I had 4 verticals, I'd have 5 sections, right?
but there's always going to be, like, in each section, there's always going to be like a part of a graph.
Something, yes. In each section, there will be some graph. Now, you might have, there may be a different problem where it does this instead. Like instead of doing this, what if we had done this and our test point here would have been here instead? So we had this test point, this one. Then what would have happened is we would have drawn it and we would have bounced off the x-axis and then come here and said, okay, to the right, oh shit, we got to go up, right? So it almost looked like a little U in here. If we smoothed it all out, it would look like that instead, right?
Would it be a quadratic?
It's not a quadratic, no, because these aren't quadratics, right? So every problem is uniquely different, right? It's not like the good old parabola. It's either up or down, vertex, and then these all have their own little unique characteristics. This vertical asymptote a lot of people have trouble with the idea of like, well, not trouble, but they ask like, where in the real world would you ever see a vertical asymptote? Something where it takes off like this. And I give you a pretty simple example. I don't know if this is a good example or not, but I think it's easy to understand, like to visualize or comprehend. Let's say we have like a lake, okay? And that lake has, I don't know, some sort of pollution inside of it, right? Like there's some chemical in there, oil's been spilled into the lake. And we want to clean the lake, we want to clean the water. Okay, so what we have here is a graph. This graph shows the percentage that's clean, where we get it to like perfectly clean water. And here's the cost. So if we want to clean it a certain percent, it's going to cost us money, right? We got to get in there, we got to use whatever, get people out there to filter the water, right? If we do nothing, if we clean 0%, it's going to cost us nothing, right? But the more we want to clean, the more expensive it gets, right? So what happens is, if you want to clean 10%, it's going to cost you whatever. This might be measured in hundreds of thousands, millions of dollars, whatever. If we want to clean 10%, it's going to be expensive. We want to clean 50%, it's going to be more expensive, right? But it's going to be impossible to ever clean 100% of the water, because no matter what you do, as soon as you say you're done, there's still pollutants coming in from rainwater or whatever, right? There's always going to be more to clean. You'll never get to 100% ever. So it becomes not, financially, it's not feasible to ever try and achieve 100% because it mathematically is impossible. It just becomes infinitely expensive. It's kind of like recycling, right? Like what we were talking about the other day. It's like the more you try to recycle, right? If you try and recycle 100% of everything, you wind up spending more money and more energy than you're saving. Kind of like that same thing. It's like impossible to achieve 100%. Make sense, kind of? All right. We only have 10 minutes. Let's get another 2 problems set up. Okay, and I'm not ready, remember there's 3 cases, right? I'm not ready to show you the other 2 cases yet. Okay, that's what we'll do next class. So I'm going to give you 2 examples. We're going to get them set up, and then I'm going to have you graph them at home, all right? And you can come back next class with it. I'm not going to ask you to turn it in. I'm just going to ask you to just attempt it, all right? So here's what I want us to look at. How about this one? X squared minus 3x minus, what do I want here? 28 over x cubed minus 4x squared. That's a cubed here. You know what? Let's just do this one, all right? Let's just do this one. We're going to get it set up, all right? First step, find out where the x-intercepts are. So to do the x-intercepts, you do what? Set the numerator equal to 0. So, I mean, I hope I've made it clear, like, how much